Cross or vector product, A cross B, little review summary. A cross B is a vector and can be used to find the angle between vectors. It's not the only way, of course. The dot product could be used for this too. The cross product can be used to find the area or parallelogram determined by two vectors, as seen in the video, and the equation of a plane in R3, which we did not discuss in this lesson. The cross product is applicable in physics problems involving torque and flux. These are two topics that you are not responsible for knowing on your examination. Torque and flux. You do not have to study that for this exam. Let's do some examples. We have vector A and vector B defined here, and I'm going to encourage you to try this. Press pause and then check out the solution. Please find the vector A cross B. Pressing pause now. And the results are as follows. You can see I followed a process in order to get the answer and memorized nothing. Example 2, please press pause after I read it and try to find the solution before having me describe it to you. Example 2, find a vector perpendicular to the plane that passes through the points P, Q, and R. Point P, 146, point Q, -251, and point R, 1, -1, 1. Please press pause now to see if you can figure this out. And the solution, as you read through, one solution is the vector -30, -15, +15. Certainly, depending on which vectors you picked, you could have had 30, 15, -15, or any scalar multiple of that would also be a vector orthogonal to the plane. Example 3. Find the area of the triangle formed by P, Q, and R from number 2 above. Again, once again, press pause and work it out. And the solution. The area was the magnitude of the cross product, and the area of the triangle was 1/2 of that. I did not bother to simplify the radical. In example 4, it's more of a proof. You want to show that a vector across itself is always equal to the 0 vector. Now, of course, you can say that A is parallel to A, and so it's equal to the 0 vector. But see if you can work this out with the actual components. Pressing pause now. And the solution is shown here. Final example is the proof of the theorem we wanted to do earlier, and here it is. We want to prove that the magnitude of the cross product is equal to magnitude A, magnitude B, sine theta. And you'll want to use some properties. I actually want to get you started with a hint. Consider this. The magnitude of A cross B quantity squared. Work with that and see if you can't do the proof. You might want to press pause now and see if you do it on your own. And the solution. This, I guess, warrants some explanation. The magnitude squared, if you recall, is the components, the x, y, z, or the I, j, k components, each of them squared, and the sum, because the magnitude squared gives us that. And then from there, if you actually FOIL out each one of these quantities, you will receive this statement here. Now, the leap of faith statement comes when I say equals here. The only way to convince you that these two are equal to each other is if you take this here expression and expand it all out, and you will find that it is equal to this expression here. So that's a little bit of trickiness, and you may have got to this point and said, what the heck? Well, that's it. But once you have this expression, then we have this first one is the magnitude of A squared. The second expression is the magnitude of B squared. And then this pretty cool expression is what mathematicians have defined as the dot product, and the dot product is squared. So that gives us magnitude A squared, magnitude B squared, and then I use the theorem from before, magnitude A squared, magnitude B squared, cosine squared theta. And then I factored out the magnitude squares, used an identity, which left me with the square of what I want. See, by me introducing this initial squared, I found the answer that I want squared, and to find the answer that I ultimately desire, I have to take the square root of that, and then it gives me my magnitude A, magnitude B, sine of theta. And that concludes lesson 2.